Hello and welcome to my edXO AS physics tutorial, the Young Modulus. So we're going to talk about stress over strain. Young Modulus is stress over strain, where tensile stress over tensile strain is equal to the Young Modulus. So force in N is F, A is the cross-sectional area, I is the initial length, and E is the extension. So now I'll write up the formula in the bottom right hand corner. So FLEA. Right. So tensile stress can be worked out as the force in newtons over the cross-sectional area, and the extension over the initial length. But you can also do it like this way: force times the initial length and the extension times the cross-sectional area. Either one of the two works. So remember the one that is more understandable to you. So it's basically the stress over the strain equations that we learned in previous tutorials. However, the Young Modulus just simply combines them. So the way to find the Young's modulus is to do this experiment. So you have a test wire, and it's really thin, and it should be as long as possible. The longer and thinner the wire, the more it extends for the same force. So you start with a really small weight, and you make sure it's nice and straight, and then you measure the distance between the fixed end of the wire and the marker, and that's your unstretched length. And then if you increase the rate, the wire stretches and the marker moves a bit, and you increase the weight step by step, and you record the marker reading each time, and the extension is the difference between the reading and the unstretched length. And when you've taken all the readings, you use the micrometer to measure the diameter of the wire in lots of different places to take an average of your measurements, and then you work out the average of the cross-sectional area of the wire. And then you can also use a stress-strain graph to find E, where the area under the graph is equal to the strain energy per unit volume. E is stress over strain, which is equal to the gradient, and the gradient gives you the Young modulus, and the area under the graph gives the strain energy. So it's the energy stored per 1 meter cubed of wire, and the stress-strain graph is a straight line, provided that Hooke's law is obeyed. More on Hooke's law in a previous tutorial. Energy is half times stress times strain, and that's all you need to know for the Young modulus. However, once you do a practical of the Young modulus, it will make more sense when you do the practical. I don't really have the equipment to show you what it will look like, but I'm sure if you do the syllabus, then you will do a Young modulus coursework or something along those lines. I've only really got questions with this video, so you can stop if you don't want any questions, but anyway, we'll carry on. A steel wire is stretched elastically for a load of 80 newtons. The wire extends by 3.6 millimeters, and the original length of the wire was 2.5 meters, and its average diameter is 0.6 millimeters. So calculate the cross-sectional area of the wire in meters squared, find the tensile stress applied to the wire, calculate the tensile stress of the wire, and what is the value of the Young modulus for steel. So another one now where you use the formula I showed you before: F over A over E over initial length, or force times initial length all over the extension times the cross-sectional area. Either one of the two will get you the modulus. So this is assuming that the Young modulus is already been found. If the stress on the copper wire is 2.6 times 10 to the 8 Nm minus 2, what is the strain? And if the load applied to the copper wire is 100 newtons, what is the cross-sectional area of the wire for the wire? And calculate the strain per unit volume of the loaded wire. So I'll give you a 5-second pause, and you can have a go. Rewind if you're stuck. Okay, hopefully you had a go. So now we'll go for the cross-sectional area. So it's pi times 0.6 times 10 to the minus 3 all over 4, or pi times 0.6 times 10 to the minus 3 all squared, and that's equal to 2.83 times 10 to the minus 7. So stress is equal to force over area, and 80 over 2.83 times 10 to the minus 7 is equal to 2.83 times 10 to the 8 and then minus 2. And S is extension over length, so 3.6 times 10 to the minus 3 over 2.5 is 1.44 times 10 to the minus 3, and 2.83 times 10 to the 8 over 1.44 times 10 to the minus 3 is equal to 2 times 10 to the 11 nm minus 2. So moving on to the next question, number 2 now. So if E is stress over strain, then we can rearrange it to make strain equals stress over E. So 2.6 times 10 to the 8 over 1.3 times 10 to the 11 is 2 times 10 to the minus 3. And if stress is force over area, we can rearrange to make area equals force over stress. 100 over 2.6 times 10 to the 8 equals 3.85 times 10 to the minus 7 meters squared. And for part C, if we times half by 2.6 times 10 to the 8 times 2.6 times 10 to the minus 3, and that's equal to 2.6 times 10 to the 5 joules per mole cubed. So that's it for this tutorial. I hope you found this useful. See you next time.